Okay, in this video we're going to investigate how to compare the strengths of two acids or two bases, and we're going to begin with the first of the four factors that we will consider, which is elemental effects. To do this, let's go back to the example of H2S versus H2O from the last video. We saw that H2S has a pKa of 7, and we know that the pKa of water is about 16. So obviously H2S is a significantly stronger acid than is H2O. The question that we really want to be able to answer now is why. And the short answer to that question is because SH- is a weaker base than is OH-. But that kind of feels like we're talking in circles right now. We need to get to a little bit better explanation of what is really going on. I can do the same kind of comparison between trifluoroacetic acid, which is shown on the bottom left in green, and acetic acid, which is shown on the bottom right in blue. And you can see that the pKa of trifluoroacetic acid is a lot lower than that of acetic acid. And so the implication there is that the conjugate base of trifluoroacetic acid, which is shown in the upper left in green, is more stable than the conjugate base of acetic acid, which is shown in the upper right in blue. But again, we're left with this question of why. So what we need to do now is try to answer that question of why. Recall that a stronger acid yields a more stable or weaker conjugate base. You know this from general chemistry. What we want to be able to do is to evaluate the strengths of a set of bases so that we can make a statement about the strengths of the parent acids. Anytime that we're evaluating base strength, there are four factors that we're going to pay attention to. One is elemental effects, two, what are called inductive effects, three, resonance effects, and four, hybridization effects. And over the next few videos, we're going to take a look at each one of these effects individually and then see how to use them together to rank a set of bases according to relative strength. In this video, we're going to look at the elemental effects. And to do this, let's go back to the H2O versus H2S example. And of course, the conjugate bases of these acids are OH- and SH-. And we saw that H2S is significantly more acidic than H2O. So let's look at what is the same and different between the two conjugate bases here. The conjugate base of each of these acids has a formal charge of -1, so there's no difference there. However, in OH-, the charge is localized on the oxygen atom, and in SH-, the charge is localized on a sulfur atom. So what this really gets to is what is different between oxygen and sulfur. As you can see that from the periodic table, they're situated in the same group, which is circled there in green. And you have to also remember that as you go down the periodic table, there's an increase in atomic radius. The bottom line is that sulfur has more room or volume for the electrons to spread out over. And we know that electrons do not like to be near one another, so having more space to get away from each other is a good thing. So compared to an oxygen with a negative charge, a sulfur with a negative charge allows more room for these electrons to get away from each other, which is a stabilizing effect. And this trend is going to hold true anytime you compare two elements within the same group column of the periodic table. So let's kind of work through this and see what does this mean about the acidities, the pKa's of these acids that we talked about. So recall that because of the increase in size, negatively charged sulfur is more stable than negatively charged oxygen. And so another way of saying that is that it's more likely to form. You're more likely to form SH- than you are OH-. Therefore, the parent acid, H2S, is more acidic. It's more likely to lose that proton and form the corresponding anion, the conjugate base. Let's try another example. Let's compare NH3 versus CH4 and try to answer the question, which is more acidic and why? So again, we're going to start our assessment by looking at the conjugate base of each acid. And the conjugate base of NH3 is NH2 minus. The conjugate base of CH4 is CH3 minus. So the fundamental difference this time is a nitrogen with a negative charge versus a carbon with a negative charge. However, this time we're not looking down a group, but we're actually looking across a period. And the predominant trend when you're going across the periodic table is increasing electronegativity. Since nitrogen is more electronegative than carbon, the nitrogen nucleus is pulling in on the electron density more tightly than is the carbon nucleus. And this pull is actually a stabilizing effect. So the bottom line is more electronegative atoms like, quote unquote, electron density more than less electronegative atoms. And this trend will hold true anytime you compare two elements in the same period or row of the periodic table. So again, let's see how this works back to the acidity of the acid. Since NH2 minus is more stable for the electronegativity reasons we just discussed, than is a C minus, it's more likely to form. That means that NH3 is more acidic. It's more likely to lose its proton and to form its conjugate base than is CH4. And if you were to check pKa values, you would indeed see that the pKa of NH3 is 38, while the pKa of CH4 is 50. So clearly NH3 is quite a bit more acidic than is CH4.